Hello everyone, welcome back to the channel. So now let me ask you something. Have you noticed how platforms like Netflix, Amazon or Uber almost never completely go down even during massive traffic spikes? Things mostly continue working, maybe slightly slower, maybe one feature temporarily stops, but the entire platform usually survives. And that's not luck, that's basically resilience. Because real world systems are designed assuming one important thing something will definitely fail. Might be server, might be network, or your service might crash. And resilient systems are built to continue operating despite those failures. So today, let's understand how big tech actually build resilient systems, not theory heavy, just practical architecture thinking. So let's get started. So let's see with a basic example. Imagine you open a food delivery app, you click view restaurants, your request travels through different layers. Now, very quickly, the first endpoint is the API, where entry point that receives your request. Then the service, where the actual business logic layer is present. Your database, where the information is stored. So the flow is basically user sends a request, system process them, the data comes back or gets stored. And honestly, at small scale, this setup works perfectly fine. But the problem starts when the traffic grows or one of the component gets fail. So the step 2 is single point of failure. Let's suppose my service currently is the only single point of failure which can happen. If service fails, the entire flow gets failed. Suddenly, everything behind it stops working. User cannot continue. This is called a single point of failure, meaning one component failing affects the entire system at whole. And resilient systems try very hard to avoid this because in large scale systems, failure is normal. Let's suppose in the next step, we introduce redundancy. So instead of having one service, I will have one more service which is has the same kind of thing it does. Service B. And this I can name as service A. Instead of relying on one service, companies create multiple copies of the same service. This is called redundancy. Now, if service A fails, traffic can move to service B, right? So if this fails, I can move my entire traffic to service B, and then from service B, I can redirect my traffic to the database. So users may not even notice the issue. This is one of the biggest ideas in resilient architecture. Never depend on one thing. Then the another concepts which comes in is the load balancer around the API layer. Now, if multiple servers exist, how do you users get distributed across them? That's the concept of load balancer. That's where a load balancer comes in actually. A load balancer is basically a traffic manager which distributes your traffic. Instead of sending all users to one server, it spreads, right? Benefits of load balancer is better performance, better scalability, and better resilience. That's the main thing. Because even if one server dies, other continue serving the request. Step 5, which comes in, is failure isolation. Now, here's a very important idea. Big systems are designed so that one failure does not spread everywhere. For example, if payment service has issues, search should still work. User should still browse products. Notification should still send. This is called failure isolation. Instead of completely getting collapse, the system degrades partially. And honestly, this is why apps like Netflix still work even during incidents. Maybe recommendations stop temporarily, but streaming gets continue, right? This is the main part of failure isolation. The another part which comes in is cache. Now let's talk about cache in a very simple definition. Cache is temporarily fast storage. Users call the cache then return a response right instantly. If it does not have a response, it goes to the database. And it also stores get the response from the database back again and send the response. Is a temporary fast kind of storage. Instead of asking the database again and again for the same data, system stores frequently used data in memory. Example, if million of users request the same trending movie list, cache can return it instantly without hitting the database every time. This reduces pressure massively and lower pressures mean better stability during high traffic. Then we have a concept of queue as well. Now imagine sudden traffic spikes. Thousands of requests arrives together, processing everything instantly can overload services. So queue helps in that. We'll discuss more in the further video on queue. Now let's connect all this to a real world example. Imagine it's a new year. If million of people suddenly open Uber trying to book rides. If the system was not resilient. Servers could overload instantly, database could slow down, requests could fail everywhere, and the entire app might get crashed. But instead, different resilience techniques start working together. Load balancer distribute traffic across many servers. Queues absorb sudden booking spikes, and the driver matching system process requests gradually instead of overloading instantly. So even if some parts slow down temporarily, the platform still mostly works. Maybe search pricing updates slowly, maybe notification delay slightly, but users can still book rides. And honestly, that's the real goal of resilient systems. Not perfection, but graceful survival during chaos. And the another thing which helps in here is timeouts plus retries. Like suppose now system constantly talk to other systems. One service may depend on another service. But what if the downstream service becomes very slow? If service A waits forever, everything behind it also gets stuck. So systems use timeouts, meaning stop waiting after some limit. And sometimes systems retry after a short delay because temporary failures happens often in distributed systems. This prevents the entire request chain from freezing. There is a concept, circuit breaker. Now imagine service B is continuously failing, calling it repeatedly only makes things worse. So systems temporarily stop sending requests there. This is called a circuit breaker. Instead of spreading failure everywhere, the system isolates the unhealthy service and shows a fallback behavior instead of. For example, cache data or limited functionality or a temporary message or maybe a partial response at some times. So, even during failures, the platform remains usable. Then also there is a concept which comes in multi-region systems. Now let's go one level bigger. What if an entire data center fails? Big tech companies don't rely on one location. They run systems across multiple regions, meaning multiple physical locations around the world. If one region goes down, traffic shifts to another region. This is expensive but extremely important for a high availability system. Now here's the real mindset difference. Company like Netflix, Amazon and Uber don't build systems assuming everything will work perfectly. They build you assuming failures will happen constantly. And that changes how architecture decisions are made. Resilient systems are not systems that never fail. They are systems that continue operating despite failure because they are built to handle those failures at every given point of time. This is a whole picture which kind of looks like. So, next time an app keeps working during heavy traffic or outage, remember one thing, there is a lot of architecture behind that stability. Resilience is not one feature, it's a collection of engineering decisions designed around failure. And honestly, that's what makes distributed systems so interesting. If this makes sense, do like the video. I'll keep breaking down the software architecture and system design concepts like this in a practical and beginner friendly way. See you in the next one.